Welcome, everyone. For today's prep, we're going to look at or introduce the idea of Green's theorem. So we'll look at the statement of the theorem and then try an example. And what we're going to see is this is really another kind of fundamental theorem of calculus, but this time for double integrals. All right, so let's start with the theorem. So we have Green's theorem here, and we have curve C. And this is, well, it has a few properties here. The big one is that it's a closed curve, so it starts and stops at the same point. And then we have region D, and region D is part of the xy plane, and this is whatever region that's bounded by curve C. So C is kind of like the edge of this region. And actually, that's important enough. Let's write that down. So C is kind of the boundary of region D. And region D is just part of the xy plane. All right, so what does Green's theorem actually say? So we have a curve, we have a region D, and what we're doing is we're calculating the line integral of a vector field. So that's what this is. This is just another way to calculate the line integral for a vector field around curve C. So vector field F in this case we're dealing in 2 dimensions. So our vector field F here has components P and Q. We're just calling them P and Q. So P is the first component and Q is our second component here. So this is the line integral of a vector field, and we saw that this is a way to calculate, one way to calculate the line integral for a vector field. So we take our P component and multiply with the X differential, and then take our Y component, Q, and multiply that with the Y differential. And this is a way to calculate the line integral for this vector field. All right, so what does the theorem actually say? Well, this line integral of our vector field is equal to this double integral over region D of the Q partial derivative with respect to X minus the P partial derivative with respect to Y. And like we said, this is really this is kind of like a fundamental theorem. So this is similar to our fundamental theorem of calculus. And if we kind of remember what that theorem says, it says if we have the regular definite integral from a to b of some derivative, well, the way we calculate this is we find the antiderivative, and then we look at just the endpoints. So in the statement of our fundamental theorem of calculus, all the way back in Calc 1, we had this one integral where we were integrating a derivative. So that's what this part is. This has a derivative that we're integrating. And what we get out, what it's equal to, involves just the boundary of the thing that we're integrating over. So in this case, we're integrating over this segment of the x-axis, the closed interval from a to b. So that's what we are looking at here, is the value kind of on the boundary of our interval. So we had this expression that relates the integral of a derivative to kind of like an antiderivative, and we're looking at just the boundary here. In this case, the boundary of the interval from a to b is just the 2 endpoints, a and b. So we just looked at the 2 endpoints. Now for our case here, this is a fundamental theorem for double integrals. So we have this double integral over here that involves some derivatives. So there's some derivatives in here. And what we're saying is this is equal to this line integral where we're looking at just the boundary of that region. So the line integral of our vector field here is kind of taking the place of this antiderivative where we evaluate at the endpoints. And this double integral of these partial derivatives, that's kind of taking the role here for our definite integral in this case. All right, so this is kind of a fundamental theorem of calculus, but for double integrals. And the notation that we use, let's talk a little bit about the notation here. So we're going to use the, when we say the line integral over curve C, we're going to introduce this idea of a positive orientation. So sometimes, rather than writing just the line integral over curve C, we might write this as with this little kind of circle in the middle of our line integral. And this just means it has positive orientation. We'll see what that means in a second. Another way we sometimes write this is, so we might write it as with this little kind of circle in the middle there of our, or we might write it as, to really emphasize that we're talking about the boundary of region D. Rather than using curve C, we use this little del with our region D, and that just indicates we're talking about the boundary. So we use this little del to indicate the boundary of region D. All right, so we'll put this to work in a second, but let's just look at the requirements for this theorem. C has to be positively oriented, so we'll see what that means in a second. Piecewise smooth just means that we can have, we can have corners to our curve, but only a finite number of corners. So otherwise it has to be, for the most part, smooth. And then a simple closed curve. So closed means it starts and stops at the same point, and simple means it doesn't intersect itself. All right, so let's look at this idea of positive orientation. So when we have a region D, so let's say these are both examples of some region D. And we have the boundary of this region. So in both of these cases, the boundary is a circle. And, well, we also have the boundary over here. Same thing. But the difference we can make is we have this curve that's encircling our region D, and we can go counterclockwise, or we could go clockwise. So there's kind of two directions that we could trace this curve. And what do these look like? So we could go this direction. Or we could go this direction. So there's kind of two directions here that we could go. All right. One of these is going to be positive orientation. The other is going to be negative orientation. And how we distinguish is we want the region D on the left-hand side of our curve. That's just the convention we take. So we use the convention that the positive orientation of a simple closed curve C is a single counterclockwise traversal of the curve. Another way to think of this is we want region D on the left-hand side. So if we imagine kind of standing on our curve here and we walk around, we want the region D to be on the left. So if we're standing at a point on the curve, region D should be on the left side of our point. And so this example would have a positive orientation because we're going counterclockwise and our region D is on the left-hand side. And this would have what we call negative orientation because we're going clockwise and it's on the right-hand side. All right, so for Green's theorem, we need our curve to have this positive orientation. So we have to go around counterclockwise. All right, so let's try an example. We're going to look at this line integral. So here's our line integral here. It's a vector field. First component is x raised to the power 4. Second component is x times y. And C here is the triangular curve connecting the points 0, 0 to 1, 0, and then from the point 1, 0 to 0, 1, and then the point 0, 1 to 0, 0. So we want to start by just kind of graphing this region. And we're told that it's a triangular region consisting of line segments. So we plot the points, all the points that we have here. And so we 0, 0, 1, 0, and then 0, 1. And then we end up with the line segments connecting all these. And so what's going on with this curve C? Well, we're going to go one time around. Okay, so it is closed. We're stopping and starting at the same point. So it is closed. We're going to go clockwise or counterclockwise around so that our region D is on the left-hand side each time we're going around our curve. The curve doesn't intersect itself. And it's piecewise smooth. So it's not smooth at these endpoints, but there's only a finite number of them. We have one endpoint here, another, and then another. So otherwise, on the actual line segment portions here, it is smooth. All right, so we can use Green's theorem. So what Green's theorem says is that the line integral over curve C of p dx plus q dy, and remember this is just the line integral for a vector field here, is equal to the double integral of the partial derivative of q with respect to x minus the partial derivative of p with respect to y. And we're doing this double integral over region D. All right, so let's actually try this out. So in our case, region D is this entire region that's enclosed by our curve C. So our curve C is the boundary, and region D is the part of the xy plane that's enclosed by curve C. All right, so the line integral we're doing is x to the 4th dx plus xy times dy. And we want to calculate the partial derivatives. So let's figure out what is the p component here. The p component is x to the 4th. And so for our Green's theorem, we want to figure out, well, what's the y partial derivative of that p component? So p partial y here is, well, it's just x to the 4th. So this is just going to be 0. And then our q component is x times y. And for our q component, we want to know what's the x partial derivative. So our q, the y partial of our, not the y partial, the x partial of our y component, of our q component here, is y. So the partial derivative of this with respect to x, derivative of x is 1, and then we just have the y left. All right, so this is going to be equal to the double integral over region D of q partial x minus p partial y. So we end up with 1 minus 0. Y minus 0, rather. All right, so we have this double integral to do. And we'll just clean that up just a little bit. And now we have this we have just this regular double integral to calculate. So, we could do this. We want to write this as an iterated integral. So to help us with that, we can draw our cross-sectional cut. Now, in this case, we can draw it either parallel to the x-axis or parallel to the y-axis. I'm going to do it parallel to the y-axis here. And this will help us figure out what the limits of integration are going to be. So we're going to write this as an iterated integral. And let's start with the y limits of integration, and then we'll figure out the x limits of integration. So for our y limits of integration, we're looking at this cross-sectional cut, and we want to figure out what's the equation of the curve that gives us the bottom, and what's the equation of the curve that gives us the top. Well, in our case here, this is a line segment, and we know the 2 points that it connects, so we can figure out the slope, we can figure out the y-intercept, and then come up with the equation. So in this case, this is just a line, and the equation is 1 minus x. So it intersects the y-axis at 1, and then our slope is negative 1. So that's how we have the negative. All right. So that is our kind of our top edge. Now the equation for the bottom edge here, well, that's just the x-axis. So that is y equal to 0. So when we look at this cross-sectional cut, the bottom edge is given by the curve y equals 0. The top edge is given by the line y equals 1 minus x. So those are going to be our limits of integration. And then we want to imagine, to get our x limits of integration, we want to imagine sliding this back and forth now. And the furthest left I can go is right on the y-axis here. So that's when x is 0. And the furthest to the right I can go is right when I get to that point, which happens at x equals 1. Now we can confirm that by figuring out where these intersect, but that's x equals 1. All right, so now we just have a iterated integral to do. So we start with our y integration. Antiderivative is of y is 1/2 y squared. And then we're going to evaluate this from y equals 0 to y equals 1 minus x. And then we'll do our x integration after that. Let's evaluate. So the top number gets plugged in first. And we end up with 1/2 times 1 minus x squared minus 0. So I won't write the minus 0. And then we can do a u sub to actually calculate this integral. So we can let u equal what's inside the parentheses, u equal to 1 minus x. And when we do the integration here, we get negative, well, we keep what's inside the parentheses the same, add 1 to the exponent. We have a 1/2 that's already in front. And then we're going to have another 1/3 in front, so it's going to be a 1/6. And then because this was a negative x, we're going to end up with a negative 1/6 here. Again, if you don't remember how to do kind of like a quick k-form integration like this, it's really a u sub. And the differential here, if we convert the differential, would be negative 1 times dx. So that's where this negative 1 is kind of coming from. Actually, this would be like 1 over negative 1. So we have our antiderivative, and then we're just evaluating. And when we plug the top number in, x equals 1 in, we get 0. And then we subtract, and we plug in the bottom number here, which we're plugging in x equals 0, but this is actually going to be the one that gives us something. And when we do that, we end up with plus double negative 1 over 6 times 1 minus 0 cubed, which ends up being 1 over 6. All right. So that's the idea here with Green's theorem, is that we can kind of go in both ways. We can use Green's theorem to help us either calculate a double integral. So if we're trying to do the double integral over some region, well, instead we can look at the line integral around the boundary. Or sometimes we use Green's theorem to help us do a line integral, and we convert it into a double integral. So we can use it in kind of both directions. All right, so we'll try a few more examples in class. So we'll see you then. Bye-bye.